Okay, guys, so ready to go. Okay, so wait, I started recording, right? Probably yes. Okay, guys, so question number one. So what is it we want to do on Wednesday? Like how many people can show up in person without
I can show up.
so in person or Zoom? That's preferred.
I can go.
Zoom
if you, yeah.
Okay, let's do in person if enough people can show up. But there will be obviously Zoom recording. So I promise that we're gonna talk about scheduler a little bit more, but the person who wanted to present, he couldn't make it to the class today. So let's postpone it until Wednesday. And then just get back to IPC. So essentially, the goal today is to hopefully go through the most of IPC and get to capability access control. Okay, let me remind you where we are. Maybe. So the idea is that we want to allow isolated processes, and most of our system is just composed of these isolated processes, right? So we don't put much in a microcontroller to communicate. And we said, okay, the best way to do it is to actually build a hybrid mechanism which combines synchronous and asynchronous parts. So how do we build a synchronous part? Do you guys remember? What's the execution model? That's essentially what you have to know. So remember, I keep drawing this pipe-like thing in a kernel, which is a called an IPC endpoint. And how does it work? What was our height?
So one process sends a message into the pipeline, and then waits for the other process to pick it up and read it.
Correct. And so essentially what we do here, we do a syscall to switch the privilege levels from ring 3 to ring 0. Then we do some, maybe some access control checks, but at a high level, what we have to do is that we have to essentially check whether anyone is already waiting on this endpoint. And the assumption is that in most cases, there will be some kind of a receiver waiting. And at a high level, what we're trying to optimize for is for cross subsystem invocations. Like essentially this guy at a high level, you will have some kind of a compiler level, which we call IDL, stands for Interface Definition Language Compiler, which generates a stub for you on this end, and a stub on this end. And essentially, this allows clients to involve servers remotely, right? And I'll talk a little bit in a second, but at a high level, the high level idea is to invoke functions, more like similar to how we invoke system calls, but across isolation boundaries, right? And so the idea is that we implement the server as a kind of like dispatch loop, which constantly invokes receive, waiting for incoming client requests, right? And essentially, it is already waiting on this endpoint. And then the microkernel essentially just performs a context switch, changing the page tables, right, from client to page table of a server, and essentially exits here. Server does the processing, and this essentially dispatches the whatever whatever, like saying, okay, sure, your IDL compiler will ideally generate some kind of a, you don't have to generate a loop, but essentially it will allow you to going from a receivable message in some high level representation, like whatever, a type or something, to go from this to something like invoking a local with respect to the server function foo, which checks some arguments A, which takes some arguments A, B, C, returns some value, and then essentially when this invocation finishes, you essentially go back with this reply invocation, and then the client gets unblocked and the cross subsystem invocation completes, right? Make sense? Does this basic story make sense to you? Makes sense. Okay, and I was saying that we probably, in order for this guy to, like, instead of like replying, exiting back to read 3 and then doing the receive again, we say, look, let's combine this primitive. So instead of doing just reply, we'll be doing something like reply and wait, for example, meaning that we're going to be waiting in a single invocation. We will stay blocked on the IPC endpoint, waiting for the next incoming message, right? And so since we said, okay, guys, we probably can have multiple, we want to support multiple clients. And we said, okay, sure, if there is another client who can also send them to the same endpoint, maybe replies can come out of order. And we said, okay, first of all, we probably can queue senders, for example, making sure that, you know, if there are multiple pending, if the server is busy, we'll in-queue replies. But also we came up with this idea that in order, like, because the server can out of order say, okay, sure, I want to reply to this specific person or to this specific client. When you send an invocation, you provide, the system can generate a specific reply capability and or reply endpoint for now. We don't talk about capabilities, right? And on a fly, when this guy replies, it will reply this reply endpoint, which will go specifically to the sender, which originally sent the message, right? It's kind of cute because you say, look, it solves you like the problem of essentially searching for who specifically, which thread gets the reply. You immediately get it to this endpoint, right? And if you carefully code it, you probably can optimize a lot, which SEL4 does. And this is basically more or less, it's a simplified view, but it's more or less a model which is implemented in this L4 line of microkernels, and specifically in their verified SEL4 version, right? And why is it important? Because SEL4 is the production quality microkernel deployed very widely in the cars, in different, like, maybe even on cell phones and stuff. I can look it up for you, like who currently runs it, right? So this is our kind of communication story, right? And the second part of this story, which we discussed last time. Okay, so do we know what kind of, for compiler people, what kind of interface definition language compiler we want to build for this? And what is that we want to, like, what is the goal here? Why do you need this interface definition language compiler to begin with? What purpose does it serve?
I'm not sure exactly, but it sounds a lot like an ABI.
It sounds like what?
An application binary interface.
I would say ABI maybe sits somewhere here, but I partially agree with you. So if you, like, essentially here we send some type which is a message type, right? And let's just quickly define it. But really, if we want to implement across subsystem invocations, which look like regular functions to the rest of our code, right? Which take normal arguments. We have to map them on those messages, right? And I would say that, I mean, I can be wrong and I'm not very precise about it. So ABI is how you map a message onto, no, you're probably right. It's essentially how you map those arguments onto a low-level representation of a message, right? So, and here obviously also, so like in distributed systems, it's called marshalling and unmarshalling, right? Because you marshal into a message, the message goes across the wire, right? In our case, instead of marshalling on the wire, we can come up with a slightly simpler data structure. And let's talk about which one. But also if we have a asynchronous communication primitive where we have like, let's say a ring buffer, and we'll discuss it in the second again, then you can really marshal long messages by kind of almost exactly how you would marshal something on the wire, right? So, okay, sure, like fine. So for a compiler person, probably building such compiler is not a big deal, right? So because essentially, like, what's involved? Like quickly, can someone tell me? So it's a big deal. Building those interface definition language compilers was a big area of research, let's say 20 years ago. Eric Eide was big on this, so he was building compilers. It's called, actually, I think it was called Flick. And I think that's why, because probably everything was starting with F, like for blocks. So, but I don't know, maybe you should ask Eric, maybe I'm. But it essentially was compiler for this use case. And the idea was how to marshal in such a manner that, and Flick was kind of retargetable compiler because people were saying that, oh, guys will go like really figure out how to, with the minimal amount of overhead, put those, let's say, integer types or something into like a message type, which people like again, is it on a stack or maybe it's somewhere else? Like you can think about it, how to do that, right? But essentially, okay, at a high level, okay, let's go backwards to that. So how do we want to represent a message here? What kind of qualities does it have? Does it need to have?
The sender and receiver, like process IDs.
But like, let me ask it differently. So how does it work at a very low level? If I were to ask you to code it up, for which we apparently don't have time anymore, but still extra credit coding up. So there is this endpoint, right? And endpoint actually can also have a few of receivers as well, right? So it probably makes sense to say, look, if we want to send a small little message between, like it's kind of like connecting the two, then we can maybe have a specific page associated maybe with a thread of execution, because there might be multiple threads running, right? And like the sender will have the same page. And essentially, like it can have a finite number of, let's say, 64 byte slots, and you say, look, roughly speaking, it's message slot or message register 0, message register 1, message register 2, right? And this is the same, obviously. And essentially, what happens is that on a send, receiver fills those in with like concrete values. The sender, sorry, fills that in, and the microkernel, like technically speaking, you say, look, I can have just a pointer to this message. That's fine, but then you probably need to also do some additional checks. Like remember, every time you go with the syscall, you have to do checks, like in x86, the checks will be something like, is the message fully contained in the address space? Is the page mapped? What happens on the page fault? That's why it's a little easier to make sure that this page is mapped upfront. And in fact, like, is registered with the microkernel, and microkernel knows that this page is around. And if, like, essentially just say, look, I don't need to do any checks. I know that this page is there. And at this point, you say, look, I pick up receiver. I know receiver's page as well, and essentially just simply copy those scalar values, like between the sender and a receiver, right? Make sense? And so then if we understand how to do it immediately, all the like different design choices are possible. And people used to have like queues of those messages, like in this famous Mac microkernel, which Mac OS is still using. Supposedly, I mean, back in the days, and I don't know whether this is fully true or not, the argument was that one of the reasons why Mac never took off, besides maybe Apple, is that sending and receiving messages was too expensive. The reason I'm kind of like distancing myself from this argument, but is that first of all, Mac actually did take off to some degree, right? And second, maybe on a slightly newer hardware, which we have today, overheads of like queuing messages is not a big deal. As long as you don't doing like allocations on the critical paths, then you probably will be just fine, right? So, but ACL4 took this argument forward and they said, look, like really, we have one slot on the receiver, one slot on the sender, and we will just swap it between them, right? Scalar arguments. And then your ideal compiler essentially, like how will it, like its job is essentially to make sure that A, B, and C are correctly mapped on and copied here in this, essentially in this prologue of this function. So you kind of say something like MR0 equals A, MR1 equals B or something, right? And you define this API interface for how to map the messages on or arguments onto the message registers and so on and so forth, right? Agree? So, and okay, so that looks like a reasonably simple ideal compiler, right? Sure, what if you have a pointer here to a data structure? Now what?
Do you need a sort of automatic marshalling scheme to fit that into one of your message registers?
I agree, and that's a design choice. So we built, my team and I, we built both because we were our research goal in this specific, in one of the projects was to essentially take existing C code and kind of tear it apart. So put half of the code on one side, put another code, part of the code on the other side, and it was specifically Linux kernel and a device driver. And we were running device drivers in isolation, right? And essentially we thought, okay, look, but Linux kernel is designed to run in shared memory. So it's not uncommon to pass data structures which essentially lead you to like complicated like hierarchies in the kernel. And you think, okay, that's a little tricky, but in practice, it's not as hard. So essentially you say, look, if you define the type of those data structures like A, and you know that A will have a pointer, and this is type B, then you essentially say, look, I will follow the pointer in A. I will first like marshal essentially all the fields of C, maybe in those messages, right? And you say that, yeah, so you can run out of those messages, and then it's your decision. You can either say that you cannot pass this data, like you can check it statically and you say like, I cannot marshal this data type, or you can start growing the number of those registers, or you can do some other tricks, like maybe you will allocate a region of shared memory, do whatever you want, right? And all of it is possible. And then of course, if type A is explicit, then you follow the pointer to B, start marshalling B, and so on and so forth. If you have doubly linked lists, it gets a little complicated, and your logic of your marshalling code, which your compiler generates, should mark and like it's kind of like you walk the hierarchy of data structures. But as long as everything is well typed, you eventually converge And you say, look, yeah, I actually like the entire tree with a cycle is marshaled, and on the other hand, on the other end of this receive operation, you can, wow, your unmarshalling code here, which says you generate functions which look something like you receive a message M and you say, look, unmarshal. Well, better probably do something like you will do something like foo. Right. It takes M, but in the end, it essentially leads to invocation of foo, right? And the code here will create the hierarchy, and you say, but Caesar points to a pointer, and this points to something else, and this points to something else, and there is a cycle. So, well, sure, like it's a little annoying, but you really can have malloc which allocates the data structure. So if this is what, if this is A, this is B, and this is whatever types, you allocate them on your local heap, you run them, you pass them to a function, you return. Immediately compiler people start like saying, okay, like the guys, like oversimplifying. So what's the oversimplification here? No, but this works, right? At least with this, you can do those invocations. And if you are in control of what can be sent across, you're not running into problems. But if you're not in control, if you're like really tearing apart piece of C, then what can go wrong? Or what will be? Tell me. I mean, I'm not a big fan of those approaches because, yeah, at some point, the number of corner cases which you encounter just outweighs all the benefits. I'll give you a couple of interesting problems. What if like suddenly like lifetime of one of those data structures outlives the function invocation? Because if A, B, and C just really live for the duration of the function, you don't even have to malloc. You can allocate them on a stack, right? But what if it doesn't? What if you actually say, look, I am referring to this B, which I used in some other in the invocation bar, and it's the same B, and really B was created here. That was the beginning of the lifetime for B. It was allocated inside the receiver, and actually when A refers to B, it actually has to refer to this B, right? Wow, at this point your life becomes, okay, sure, still kind of a case to publish, but I wouldn't build systems this way, right? So do you agree with this? Lifetime is a bitch, like for real, like especially if you want to say, like, because now you have to somehow track lifetime objects across isolation boundaries. And also maybe if it's like a reference counted lifetime or something like this, right? It's still probably doable, but it's not fun, right? And it's very error prone, right? So tearing the code apart is not fun. And so, but I just wanted to make sure that we understand that people were trying to do, like, yeah, don't forget to talk to Eric. What is it called? Flick? Or Flick, something like this. But just talk to him, like, Eric, how did you manage lifetimes across the isolation boundaries? But okay, so but for small data types, maybe we say, look, we only pass like plain old data structures, like no pointers. That's a reasonable design choice, right? Or like, and you design interfaces in such a manner that foo does not take an object hierarchy, because you can imagine that there is a ton of attacks. So, for example, you can somehow reorder those functions and say, look, you never called bar before, but foo believes that B was allocated, and actually just simply says, okay, there will be a pointer to something, but it can lead to those attacks. Obviously, you can marshal most of C, right? So you can marshal linked list, that's easy. Like if you have arrays, sure, if you can know that, like marshaling something like buffer and len is a little, it's not hard on its own, right? But it's hard when you tearing the code apart and you cannot trivially figure out the dependency between buffer and len, right?
So if doing this in Rust, do you think that a library like Survey would do the trick?
Most likely, there is a collection of those different libraries in Rust, like which essentially build procedural macros probably to implement this marshalling, right? So you don't really need to build a compiler. I looked at Certa, but a while ago, and I looked at a couple of those, but that's one way to go. In the end, I think, again, I always opt for like a real compiler because there will be a ton of corner cases and debugging procedural macros is not fun, but like people do use Certa, right? So it works. So it's a marshalling library, which just does it in Rust. Yeah, in Rust, maybe no. But okay, as a systems designer, I would say it's not a good idea to build this API based on a specific language, right? So it should be language agnostic. So for example, there is a popular, in distributed systems, there is this like Cap and Proto, or like Google, whatever, protocol buffers are popular libraries, but they are kind of language agnostic, right? So you have a high level, you have an interface definition language, which allows you to specify bindings from different languages into like low-level representation and then build like this, right? We like just wanted to illustrate a couple of, I forget what was my line before I got distracted, but essentially the most, okay, who can guess the most painful feature of C for marshalling? Hi, I was saying that buffer land, okay, sure, strings not a problem because we know it's like a sentinel array, so we know how it ends. But in C, like there is a real, the type which is a real bitch.
Pointers, they just don't carry enough information, unlike Rust, to be able to reconstruct it without, like, I don't know any way that you could generate an IDL for C, because its types are just too weak.
Yeah, so for example, like when we were doing it in Linux kernel, the Linux kernel says, okay, something like net, struct net or something, and then it has a nice field which is void pointer private data structure. That's the way to represent polymorphism in C. Say, well, depending on whatever your device net is, like it can be different type, right? And you have to somehow, like we actually built static analysis, which like essentially pretty reliably enumerates all possible versions of this type and then like encodes the type and says, and then goes on and marshals modulo the error that we miss, like it can be A, and the real pain comes is when it becomes dynamic and you like on one execution path it's A, on another it's B, and then you cannot even like statically detect. And my type, which I was talking about, is in C it's called the tagged union. So essentially in C, like if you want to build an option type, they say, look, build the union and it will have a tag field. But it's a convention kind of, and then you say union, and based on the tag, I can do some number. It's either this type or this type, right? It's literally an option, but type, or an enum type in C. But yeah, it's almost, this is even a wilder version of it. But the point is that typically the number of options is smaller with the void type, so it's easier to deal, and with the tag, this list of unions can be pretty long. So that's painful, but you can still do like you can restrict a little bit what can be passed across and stuff like that, but more or less, yeah. So essentially, you need like we call it, I think, a discriminator function, which here you say, look, someone has to write a function saying based on this tag, that's the type, and then goes on with marshalling, right? So that's not fun, but okay, you don't have to, like, if your goal is not to support like vanilla C, then you can make sure that all of it follows specific set of conventions. You can restrict types which you pass across, you can introduce tags, but maybe they will be explicit and stuff like that. And still like write meaningful code within this model, right? Make sense? So any questions about it? So, and essentially what I wanted to say, like, more or less any microkernel which you will pick we'll do something similar underneath. I just wanted to make sure that we all understand that this is really happening, right? Okay, so this is the synchronous IPC. And as I was trying to convince you that it's fine, and it's fine for implementing those function invocations, but really the overhead of going into the microkernel and switching the page table, which is like, you can remember the number around 1,000 cycles, is too expensive for any meaningful communication, right? And so obviously people understood that it's not a very good way if you essentially you have some kind of like a TCP stack on one end and the network device driver on the other, and you want to send packets, like every time going through a microkernel is not a good idea. And so we talked about it. So what do we do in this case? How can we optimize this IPC communication mechanism? What was our...
Is it by shared memory?
Right. So we said, okay, sure, we can make this observation that we can separate control and data planes and say, look, you establish communication between these two isolated subsystems just once in a while, and that's your control plane. And then you send a bunch of data, and that will be a data plane, right? So how do we want to organize this data plane, right? We say, look, sure, we will roughly split this shared region into two logical regions, although they can be mixed together, right? So it's going to be one continuous region or something. And one will be this metadata region, which will be tracking available like messages, like actual payload. And the payload is that probably we want to copy from the sender into the shared buffer and from the shared buffer into receiver, unless we have some kind of guarantee about the lifetime of this object, and so receiver may be completely cold without even like without deallocating it, right? So, and then what essentially we traded, our trade-off was is that instead of going into the microkernel, doing the context switch, going up here, going down here on the reply pause, doing context switch, going back here, roughly everything is taking 1,000 cycles. We traded for a copy. Essentially, we say, look, as long as this guy copying this here and copying maybe out here is less than this 1,000 cycles, maybe that's a viable scheme, right? So for sending reasonably, like a typical data center packet is like 1 kilobyte from some sigmetric studies. Like copying 1 kilobyte is probably roughly like, let's say 50 cycles, right? Just because it's all like vectorized instructions if you want, so it's reasonably fast. MCPI is well optimized, right? So 50 plus 50, 100 cycles. So we're clearly winning, right? Make sense? So this scheme works as long as the copy as long as the object is large. What happens if the object starts growing? Like megabytes. What do we do then?
Can we grow the shared memory?
Can we do what? Grow them?
It seems like it would be too large to fit. So either
No, imagine you can allocate any size, 128 megabytes or anything. But
Have both strategies.
have both. Okay, so how do you want it to work? So what do we do with the large object? So clearly copying the large object becomes like a pain.
You just split the large object into chunks.
So, but then it's like associativity. No, what is it called? Like you still will end up copying all of it, right? So even if it's small chunks.
Okay, maybe this is crazy, and it probably is, but is it possible to give the other process to modify its page table to give access to that chunk of memory and only that chunk of memory? And I'm talking about not the shared portion, I'm talking about some way to eliminate most of that. Giving access to the original payload.
Yeah, and this is how it was done. So specifically, microkernels were evolving for a while, and they were evolving towards this use case where you have a system composed of small subsystems, like I mean, client and server. But then, like, there is a paper, the title goes something like, "Virtual machine monitors are microkernels done right." What it means is that at some point, virtualization figured out a similar use case where instead of just running a TCP and a NAT like a device driver, it just essentially just runs the whole VM. VM-A, like it's your VM, your Windows VM. And really there is a device driver like a NAT device driver, which runs in some device driver VM. So VM device driver. And at this point, the characteristics of this APC mechanisms changed a lot because microkernels were more geared towards sending a lot of small messages. And in VMs, it was not uncommon that you send either a ton of small packets like we just talked about we talked about this shared ring buffer. And essentially the idea of this shared ring buffer came from the domain of virtualization, honestly. But then also, like their second use case was sending large objects. Like if you have a disk, then often you save, or like a file system, you maybe like send parts of your buffer cache, which are giant, or like even to the whole files. And Xen, which was arguably the first production quality, low overhead virtual machine monitor, introduced this idea that you can either temporarily remap this payload into the receiver. Like essentially, like, of course, it requires exit into the microkernel, updating, like essentially updating the like figuring out which physical pages map this virtual memory, accessing the second page table, and essentially mapping the same pages here, right? But again, if this operation takes smaller or less cycles than copying, then it's a viable approach, right? And so they came up with a slightly different IPC construction. It was slightly different IPC interface. It was like, roughly speaking, you can just go into a microkernel and you say, okay, so how to build it? You can still build it on top of a SAN primitive, right? It's just that you somehow have to identify this region, and you say, look, I draw this symbol because this is how people draw capabilities. And we'll talk about capabilities, but it's just roughly speaking a pointer to your own memory. And then you say in this message data structure, which we discussed, you say like regularly I have message registers, let's say 32 or something for scalar values, but also you have capability registers, capability 0, so let's say capability again 32 or 31. And if you say that you passing something here, it's the intent is that this thing the guy on the other end can actually receive it in their own kind of message data structures, which has also like a scalar part and a capability part. They can say, look, I'm ready to receive a region of a specific size, and you have to agree at the application level, like what size you are ready to receive. But essentially you say message capability 0, and here when they meet on this IPC endpoint, the microkernel kind of like essentially does the mapping, remapping this memory, allowing the receiver to essentially map those pages, right?
There's an optimization with forked processes where they share the same page table until the first write. Can something like this be applied to this problem where, like, when you receive it, if you only read it, you don't need to actually copy the data because you're just treating it read only? Because you are kind of sharing the same memory at this point, so
right. So
it would be bad if
the physical memory sits somewhere here. Right, and this is the region that's mapping it from sender and receiver.
Yeah, wouldn't it be bad if the receiver like modified it, right?
That again, that depends on how you want to structure this communication protocol. If you're granting the read-only access, so for example, here maybe your capability says, okay, you can only map at read-only, sure. A funky interface which Xen introduced was a flip operation. They say, look, because we're constantly doing it. And okay, their use case was that if you have a device driver VM which implements access to a device driver, and you have multiple clients which try to receive from the device driver, the incoming requests can be in some undefined order, right? So you say, this is A, B, and C. And you say, look, they came as B, C, and A. And you say, what you say here is that the flip operation says kind of like, because normally when you do a receive, you say, look, provide, here's a page and receive into this page. But since if there is a predefined receive page, then you have to marshal and do a copy, right? From like some internal receive buffer to this page, which is mapped into A. And if you do a flip operation, you say, look, if you give me some region of memory and this receiver is for you, I will just flip, and your memory can be used later to receive for some other VM, right? It's kind of replaces it. Maybe it will, if it not will be for A, it will come for C, but you always have this balance that you give a page, you give a region of memory, and you get the region of memory, right? It's a flip operation. You get the point, but then you have to kind of like you receive one packet and you restock dynamically a buffer for the incoming packets, which are added to the DMA queue and will be filled in. But your buffer might end up the data which comes into that buffer might go to a different data, right? You're saving a copy of this. That's kind of cute. So, but anyway, but we got how map works, right? And you say, look, we can kind of change our IPC mechanism to allow sending pointers to memory regions, right? Makes sense? And then, like in this more simple scenario where there's no flip, you say, look, like the receiver has to essentially provide a pointer to a virtual memory, or you can structure it differently, but then microkernel have, like, if you don't provide explicitly a virtual address, then the microkernel has to figure out which virtual address to use. That's additional logic, potentially more bugs in the microkernel, but also like some unpredictable performance, because you might structure your address space in such a manner that this search will take longer than expected, and then you don't have a real-time guarantee, and the whole system will, you forgot like to steer you will not be able to run a real-time process. So ideally, you should avoid it, and instead you say, look, this guy says, well, its virtual address should be unmapped. If suddenly there is a bug in the address, part of this region is already mapped, you just abort, but at least you have constant time guarantees, right? Make sense? So sure. So that's essentially gave them like essentially from entering the microkernel on each invocation to doing copy for small packets to remapping pages if remapping becomes faster than copying, right? Makes sense? And remember, I mentioned that device, which I mentioned it last time. I'm pretty sure it was called Solar Flare. Solar Flare was a company that the hey guys, they identified that this is a hotspot in virtualization, and they said, okay, copying this stuff takes too much CPU time. They were manufacturing a physical device where it was actually doing a DMA from the sender to the receiver in using the hardware of this device. They didn't last it too long. The Solar Flare had different products, so probably just they probably in the end they were selling network interfaces, right? But at least they tried to accelerate the copy between sender and receiver in hardware. Okay, so this is nice. So one other additional detail here is that how to structure this metadata region, right? I mean, there's a couple of problems here. So one problem is that, okay, let's just think about it. So what is this metadata region? So how do you want to like build this IPC mechanism in terms of specific data structures which you share between the sender and receiver? What kind of data structures do you want to use?
Is it a queue?
It's a queue, but what kind of properties do we want?
Well, you've got either side. Well, actually, there could be more than two sides. Any client could be sending or receiving, waiting. So there needs to be some sort of a wait queue. And then for messages that have been sent, another queue, perhaps the same queue, for messages that haven't yet been received.
You lost me on the second part, but let me quickly, push back on the. Okay, you're right. The very first design choice you have to make is whether it's a single producer, a single consumer, or multiple producers. Single means that there's only one line here, or multiple producers, multiple consumers. And it turns out that the overhead of having to log here to make sure that multiple producers, multiple consumers can receive and send is prohibitively expensive. Like it's just so expensive that it just kills the whole scheme. And does anyone know the answer why?
Just contention, like low contention.
Yeah, low contention on what? But can you like elaborate a little?
Oh, like because like with any data structure like this, what you basically need an agreement on is which index in the queue has been filled most recently. So when you have multiple producers who want to all at the same time, they will all be fighting over that one index in the queue, which could lead to like if you're using compare exchanges, then they might keep failing.
Correct. And maybe your implementation is even more involved than mine, but let's just imagine for a second we have just one single log, which allows, for example, or let's say producer log maybe. If we have multiple producers running on multiple cores in parallel, the contention for this cache line, what it really means, so typically you say, look, if you do some kind of atomic exchange operation, which essentially needs to acquire this cache line in an exclusive state, right? Which means that it has to send it, if this cache line was accessed, locked on the other core, it has to send a request to this core through the cache coherent protocol, get it back, and roughly, like depending on where you are in the hierarchy of the CPUs, whether you are on the same die or across the die, on the same die, it's probably something like 80 cycles or 50 to 80 cycles. Across the die, you add another 200 cycles, right? So just to cross the cross socket link, or maybe plus 250 or something along those lines. So just even to enqueue a single message, because the probability of you holding this line is so low because everyone is trying to push into this queue under contention, that you immediately add those cycles. And as I was saying, I think it grows actually linearly with the number of senders. So there will be also like some constant n here, which roughly like in case of 10, it's already like 2,500 cycles, right? So essentially it's longer than just going through the microkernel or anything, right? So that's why multiple producers, multiple consumers quickly disappeared from those designs, just because the contention. And I mean, the key, and we might want to talk about it later, the key is that, I mean, no matter how hard you try, whether it's an atomic log or whatnot, as long as you're contending for the same cache line, there's this n factor here. if you're contending for different cache lines, you're just paying the price of cross-socket links, which is also not super low, right? So for example, you can build scalable logs where this cache lines can be attached to individual cache lines and then n disappears, but still enqueuing is expensive, right? Okay, so now we say, okay, look, our queue will be single producer, single consumer. So can you build me the most efficient single producer, single consumer queue? Meaning that one producer feds the messages to the queue, one consumer picks them up. So at this point, you don't need any synchronization, right? In theory.
So does this mean if you want NPMC that you have to do the locking yourself in user space code?
Probably because you don't even want to go into the microkernel to save the overhead of syscall, and it will not help you. I don't think it will help you in any manner. So user level protocol will be as efficient as a kernel level protocol for locking, right? But the goal is to avoid locking altogether. So how to do it?
So metadata wise, we need a head pointer and a tail pointer.
Mm-hmm.
So producer will write to the head and producer tail, or vice versa. And in terms of the operations themselves, it will be like message passing litmus tests. So you write the data, do a release, write the data and then do a release store for the index, and then you do a load acquire on the consumer index. And
okay, so like I agree with you, but let me explain for everyone. So typically the data structure, which is called the ring buffer, is used. It's just an array, but all operations on the head and tail pointers are modular the size of the array. So element 256 is mapped to 0, right? Again, right? So, and like when everything is empty, the head pointer is pointing to 0, tail pointing to 0, for example. When producer starts adding elements, they just write into the head pointer, and okay, maybe you wrote like 4 things and you advance the head pointer, right? You can write as long as head is not equal to tail, right? And so you're only like, you check for head not equals to tail. And if so, you have space in the ring buffer, right? And all the operations, like when you do plus plus, you modulo 255. Sure, and this is how x86 pipe was implemented, right? Remember? And the tail is essentially like here on the receiver side, you say, look, tail is not equal to head, means that there is some data in the buffer, and you start picking it up, and the tail start following the head, right? And so like essentially as long as they are not equal, it means that there is something in the ring, right? It like guarantees that there is no synchronization. You simply do comparisons, you advance the head and the tail, and so it moves reasonably fast. Agree? What's important here that there are no allocations, obviously, on the send and receive pass. We allocate data internally in the ring buffer. It changes a little bit because if remember in this diagram, I say, look, this might contain a pointer to a payload. And then we kind of need to allocate memory here from maybe a different a different area of this shared ring buffer. And what's the reason for doing this? Like, if we know that all messages are the same size, we can just put the payload within the ring itself, right? And we only need to do these allocations when messages are radically different in size, meaning that wasting memory for the max allowable size is prohibitive, right? Then you need to build a tiny memory allocator on top of this shared region, right? That's not fun because the moment you have an allocator, like it's like we discussed in the homework, right? So you really need to build a fast allocator. If you build something goofy here, then you're losing a lot of time on like just allocating and deallocating, right? But and again, in most cases, like for example, in the case of let's say like disk, it's easy. You say, look, 512 bytes blocks or whatever, 48 bytes blocks. So that's easy. In case of networking, you can max the NTU size or something along those lines. So you might be wasting space on like, or maybe you can say, look, my device supports an NTU, I don't know, like 1 kilobyte. It's not fun. But you got the problem that you sometimes have to allocate, right? That's fun. So we built this data structure, and it's brilliant. It was again used in all the Xen IPC mechanisms, like exactly this one: single producer, single consumer ring buffer. At what point this data structure becomes suboptimal? It's really a question about like cache coherence and synchronization. And it's not ideal. So what's going on here? Although it looks ideal, there are no locks, but still. That's a good comment. Slightly not related to what I was asking, but good on its own. So you say, look, what about bursts? Like essentially, what if like consumer does not catch up with producer? At this point, yes, you have a couple of design choices. Once you can actually build a resizable buffer, not ideal, but possible. But typically you try to make it large enough to hold enough, something what is called like, what is it? Bandwidth delay. What is it? Product. So essentially you say, look, if I know that the max delay for the consumer is such and such, let's say like, I don't know, 10 milliseconds, then, and the burst can be defined by a specific bandwidth, my ring buffer should hold enough data to multiply by the bandwidth, right? So then at least, you know, and this is that you can hold enough packets to suppress most of the bursts, right? But although they can happen, but statistically happen very rarely. And it's the same in Linux network stack. So you have to configure your receive queues to essentially say like, yeah, I have like, you know, I might not be able to receive all these packets. So just make sure that you have this delay bandwidth kind of product. So yeah, if you network delay or not network, okay, whatever. But yeah, so yeah, you have to size the queue appropriately, right? Or make sure that consumers and producers are balancing that, you know, same number of threads or something along those lines, or like some proportion between them. But in terms of this communication mechanism, this data structure, what is the bottleneck of this data structure? Let's put it this way.
You said cache coherence. Isn't that a problem when you have more than one CPU trying to access memory?
No,
we were talking about that a couple of classes. Yeah,
there are only two CPUs, producer and consumer, right? Roughly speaking, yes. I say yes to your question, answer yes. But what operations will trigger like a bottleneck or a performance slowdown? And it's okay, like if you guys never reasoned about it before, that's totally fine. But let's observe the following, that they both do some kind of a comparison of head not equals to tail, right? And imagine they both run some kind of like a tight loop, like run to completion loop. Every time you do this comparison, even if there is nothing in a queue, right? Or if there is anything in a queue, essentially this read of the head, for example, requires you to acquire this catch line in a shared state, right? And so when this guy, who might also be running a tight loop or run to completion loop, keeps adding packets to the queue, it constantly wants to do head plus plus, right? So which means that it has to have this cache line in the exclusive state. In order to do this update, it goes here, says, okay, invalidate this cache line, this goes to invalid. This gets at an exclusive state, does the update, becomes modified state, everything is fine, but this, meanwhile, this guy does another iteration of a loop because it doesn't have anything to do to receive messages. It says, okay, well, let's do this comparison. It says, okay, I don't have it, that's an invalid state, so it tells, like, okay, give it to me. Maybe this will trigger a write back to memory, but essentially it will, in some cases, it will downgrade either to invalid or to share, depending on how protocol is implemented. And so, okay, it's back to share. This guy gets it in share. Wow, maybe just received one message, honestly. And then it goes on again. And so, like, as I was saying, so how long does it upgrade from S to, from invalid to S states? For how many cycles? I just mentioned. Compiler people need to know this as well. Otherwise,
It can be just retro cycles, but protocols.
well, yes, I agree with you. If you were, okay, let's observe. If there's two threads are running as hyperthreads on one single core, they share L1. Then roughly speaking, this update might even take you, like you say, maybe just a few cycles, maybe like 10. Although I have to double check if it doesn't have to go to something else. But let's say 10 cycles, but this is very rare. And if you are not sharing L1, so you're running somewhere here, and you're not sharing L2, you might be sharing L3, and then it grows to this number, which I mentioned, like 50 to 80 cycles, roughly, because the communication goes to L3, L3 goes here, this replies, this goes back, right? So it's very rare that your communication can be, you're already in the same cache, if I understand correctly. So, and actually, that's good that you kind of like, I don't know the answer here, I should doubt myself. But you got it. So even if you like on two cores of the same die, suddenly you're paying 50 to 80 cycles. If you're going through a cache cross-socket link to another die where there's shared L3 and then L2 and then L1, then we add roughly 200 cycles here, right? And again, depends on the architecture, but roughly. So, and which means again, we're back to this, like adding a single element roughly takes you like 250 cycles. In a case when the consumer runs concurrently with you and tries to like check this condition, maybe not every time, but maybe every 2 times or every 3 times it checks, right? You got the problem, right? So the problem is that those 2 pointers are completely shared between, and like shared, not just like occasionally, but on every send and receive operation, they both try to access those pointers, right? And one of them is writing, changing the state to modified or exclusive, and another is reading, bouncing it back to shared, right? And that's fine. So Xen was running this protocol for a while, and then I think they still run it. Actually, like VirtIO probably still runs it. But because they say, okay, guys, 200 cycles, never mind. There's so many other overheads. But like there was a research community which said, okay, guys, we can solve this problem. So how to solve it? How to design this communication mechanism in such a way that there is no contention on the head and tail pointers. Well, it's so
I mean, if we know that there are multiple messages on the queue, then we don't have to read head every time
right.
to do the size check. So maybe if the producer has done has inserted one message. And it knows that the gap between head and tail is greater than one. Then we can set a new flag, which just says that there are messages pending. And only, so if the pending one is set to true, then you can just keep reading without, looking at head.
This optimization actually was implemented. So they moved from, now they introduced two heads. Like a private head, like allows you to add a batch of requests to the ring without advertising it to the consumer. So essentially the private head stays unchanged. You add a batch and then only you update the head to jump, which kind of amortizes all this cache line bouncing, right? And that's essentially what Verteo is doing and Xen is doing. And that's a reasonable optimization, especially if you add in batches, then you touch the head every like 8 or 16 accesses. Reasonable. However, of course, like people immediately started thinking about it and they said, look, let's build a ring in which there will be like a special null element. And you essentially, instead of having this head and tail, you're just essentially just moving the null pointer in the ring, like special whatever, special value 0 or something. This way, you just literally check, okay, if I have a null here, that means I have a space. I mean, if I have like maybe all of this stuff to be null, and consumer have to like make sure that those are null. But essentially, when the consumer writes into those, you essentially just update the elements of the ring itself, no shared pointers. Meanwhile, consumer comes, as long as you're separated by the cache line, you essentially pick up the messages from the ring, updating it back to something like null. And essentially, if you're running at the same speed, you never conflict on a single cache line.
So then one side only uses the head and the other side only uses the head.
Kind of, yeah. And they synchronize by explicitly inserting the content saying the element is available. Like essentially, and you can design different schemes, but essentially at a high level, the idea is that if you're separated by at least a cache line, and you can start prefetching obviously cache lines and saying, okay, I'm about to access the next one, let's prefetch. And then it almost comes down to 0, as long as the producer and consumer are moving at about the same time, at about the same rate, right? So this solves the conflict, right? So, and there is a whole line of research on how to build those queues. I think this specific variation of the queue was built by a researcher from, I think, Colorado Boulder, who visited us, gave a talk when I was a student. So that's why I remember kind of vividly. But then I came back to this work several times, and there are like a ton of like work on building those queues. Like in the end, like even how to avoid conflicts in this null elements and stuff like that. But yeah, it's worth knowing if you're really in that field of this cross communication. Okay, so that makes sense. And I think it more or less covers everything, because as I said, like essentially what you have to remember is this optimization with a private head and a global shared head. And this is, I think, what Verteo is running, so which became like a de facto standard for this communication. So this mechanism with this ring buffer is kind of like what VMs are running today. Okay, cool. Everything is nice. So essentially this is like synchronous plus asynchronous mechanisms are what we use today in those microkernels. And let me just spend this last 10 minutes, or how much? Maybe, on yet another idea, which is still kind of like still a research idea. So I mean, people are trying to build stuff like this, but there is no consensus yet. Like in this model in which I was describing, the execution model of the whole thing was a little awkward. So like, if you want to invoke a function foo across the isolation boundary, you kind of have to create a thread which runs a dispatch loop and essentially like you drop into the kernel. The kernel's like back to synchronous. The kernel like synchronizes the sender and receiver. Receiver dispatches, runs foo. And you say, look, it's a little awkward. Like, I don't even know. Like, I have to scale up. So, for example, if suddenly the number of clients becomes a lot larger due to some like bursts and whatever requests or something, you somehow have to scale this dispatch loops and in order to catch up, right? So you don't know really what to do it, but essentially, like at some point you say, look, why is it I'm really trying to scale this way, like running those dispatch loop is if semantically what I really want to execute is just invocation of this spool, right? And especially you say, look, what if like I build some newer hardware, which kind of like, imagine you have a magical primitive, which allows you to switch address spaces at the, I don't know, overhead of like 0 to 50 cycles, right? Then you don't say, look, like, I don't want to go into the microkernel, don't want to synchronize on this endpoint, don't want to go here, don't want to run this dispatch loop. Can I just like essentially like implement some trampoline code, which might jump into some intermediate level of trusted computing based TCP, and then jump back here, but it looks more logically like a single thread of execution versus we kind of stitching two threads from two different address spaces with a synchronous invocation because only one of them is running at any given point of time, right? But essentially your idea, because imagine building a web browser or something and plugins are isolated, a thread of execution, T1. Logically, I just want T1 to continue in this address space, right? So can we build this execution model without a dispatch loop, but just like kind of like jumping from one address space to another? This, by the way, there are different names which for this mechanism. One of them is called, what is it called? Migrating thread model, because the threads migrate from one address space to another. And since Talia is our historian now, so Jay and his students were working on adding this migrating thread model to Mac microkernel. So you can look it up, and essentially instead of sending messages, they said, okay, we're gonna patch the Mac microkernel to implement this invocation primitive. Another name for this mechanism is exitless invocation, because you say, look, I'm very carefully designing my isolation mechanisms. I don't have to exit from ring 3 into ring 0, but can like maybe this hardware like magical switch primitive, some new instruction which we'll come up with can switch the address space instantly here without dropping you into the microkernel, which like again, our goal is to kind of reach 0 here, right? But what is like, how can we build this mechanism? Like, for example, just to make it concrete, if you're doing something like software fault isolation, I don't know if you guys are familiar, but obviously it's one ring, right? So, and it's really can be just a switch of some kind of a tag. Software fault isolation is like binary rewriting, kind of, what is it, WebAssembly style or Google Knuckles style, pre-WebAssembly, right? So you guys should know WebAssembly, right? Or for example, we are, what is it I wanted to say? Like, or even Rust, like maybe, what if it's in Rust and it's just safe Rust and it's just invoking the function? In Rust, it's saved, like solved, kind of almost, right? But not fully. Okay, but like back to hardware. So how to build this?
Well, I presume the page tables, like, it wouldn't be as simple as our project with the kernel. The page tables, thread 2 couldn't access thread 1's virtual memory.
What? But what if you wait? Hold on. Sorry for interrupting, but imagine you have a table of page tables, and you register them somehow with this table. And you say, right now, some page table is active, but when you do a switch, I'm switching to number 1. And the next instruction after this is actually executing on a different page table, which means that this instruction is in this address space. In fact, this mechanism exists on Intel. It's called vmfunc. So the instruction is vmfunc. It stands for VM functions. It's Intel introduced like this special instruction, which they said, okay, will allow them to extend functionality of hardware supported virtualization. Like you can kind of call out, and instead of a page table, they switch extended page table, which is like a nested page table under the VM. But the logic is the same, right? So this vmfunc is there, and it just picks the next. I forget exactly what the encoding. I think like kind of one of the registers, EAX gets the index into this table, and you say, okay, I will switch from one to another, and really the next instruction after the vmfunc executes it on a different page table, although it's a nested page table, but like it's the same as the page table, right? So imagine we have vmfunc, which is very real in terms of like almost the hardware is almost there. So then what do we have to do? How our IPC will look? What do we need to move execution from one to another? Compiler people are ready to compile. Okay, let's stop here. But we will come back on Wednesday, and you guys agreed to come in person. So will it help if I bring pizza on Wednesday? Morale will go up. Good, I'll do pizza. How many vegetarian people do we have? Or non-meat eaters? Just one? Okay, and me. Okay, so we'll have one tiny vegetarian pizza for us, and then everyone else, and then a couple of minutes. Okay, good. I'll send you, like, see you on Wednesday. Let's I'll cover a little bit of this active class. The reason is that you really like if you talk in terms of like WebASM and stuff, you need to know how it works.
Even with experience, hey, I was